The whole point in learning differential equations is that eventually we want to model real physical systems. I know everything we've done so far has really just been a toolkit of being able to solve them, but the whole reason is that because differential equations can describe a lot of systems, and then we can actually model them that way. And we know that in the real world, everything isn't these nice continuous functions. So over the next couple of videos, we're going to talk about functions that are a little bit more discontinuous than what you might be used to, even in kind of a traditional calculus or a traditional pre-calculus class. And the first one is the unit step function. Let's write it as u, and they'll put a little subscript c here of t. And it's defined as when t is, let me put it this way. It's defined as 0 when t is less than whatever subscript I put here, when t is less than c. And it's defined as 1, that's why we call it the unit step function, when t is greater than or equal to c. And if I had to graph this, you could graph it as well, but it's not too difficult to graph. Let me draw my x-axis right here. I'll do a little thicker line. That's my x-axis right there. This is my y-axis. Y-axis right there. And when we talk about Laplace transforms, which we'll talk about shortly, we only care about t is greater than 0, because we saw our definition of a Laplace transform, we're always taking the integral from 0 to infinity. So we're only dealing with the positive x-axis. But anyway, if by this definition, it would be 0 all the way until you get to some value c. So you'd be 0 until you get to c. And then at c, you jump, and the point c is included. X is equal to c here. So it's included. So I'll put a dot there because it's greater than or equal to c. You're at 1. So this is 1 right here. And then you go forward for all of time. And you're like, Sal, you just said that differential equations, we're going to model things. Why is this type of a function useful? Well, in the real world, sometimes you do have something that essentially jolts something, that moves it from this position to that position. And obviously, nothing can move it immediately like this, but you might have some system, it could be an electrical system or a mechanical system, where maybe the behavior looks something like this, where it's, maybe it moves it like that or something. And this function is a pretty good analytic approximation for some type of real world behavior like this, when something just gets moved. Whenever we solve these differential equations analytically, we're really just trying to get a pure model of something. Eventually we'll see that it doesn't perfectly describe things, but it helps describe it enough for us to get a sense of what's going to happen. Sometimes it will completely describe things, but anyway, we can ignore that for now. So let me get rid of these things right there. So the first question is, well, what if something doesn't jar just like that? What if I want to construct more fancy unit functions or more fancy step functions? Let's say I wanted to construct something that looked like this. Let me say this is my y-axis. This is my x-axis. And let's say I wanted to construct something that is at, let's say it's at, let me do a different color. Let's say it's at 2 until I get to, I don't know, let's say it's at 2 until I get to pi. Until I get to pi. And then from pi until forever, it just stays at 0. So how could I construct this function right here using my unit step function? So what if, let's see, what if I had written it as, so my unit step function is 0 initially. So what if I make it 2 minus a unit step function? Let me say 2 minus a unit step function that starts at pi. So if I define my function here, will this work? Well, this unit step function, when we pass pi, is only going to be equal to 1. But we want this thing to equal to 0. So it has to be 2 minus 2. So I'll have to put a 2 here. And this should work. When we're at any value below pi, when t is less than pi, here, this becomes 0. So our function will just evaluate to 2, which is right there. But as soon as we hit t is equal to pi, that pi is the c in this example, as soon as we hit that, the unit step function becomes 1. We multiply that by 2, and we have 2 minus 2, and then we end up here with 0. Now, that might be nice and everything, but let's say you wanted for it to go back up. Let's say that instead of it going like this, instead of it going like this, let me kind of erase that by overdrawing the x-axis again. We want the function to jump up again. We want it to jump up again at, let's say, at some value. Let's say it's at 2 pi. We want the function to jump up again. How could we construct this? And we could make it jump to anything. But let's say we want it to jump back to 2. Well, we could just add another unit step function here. Something that would have been 0 all along, all the way up till this point. But then at 2 pi, it jumps. So it would be, in this case, our c would be 2 pi. It's our unit step function. We want it to jump to 2. This would just jump to 1 by itself. So let's multiply it by 2. And now we have this function. So you can imagine you can make an arbitrarily complicated function of things jumping up and down to different levels based on different, essentially linear combinations of these unit step functions. Now, what if I wanted to do something a little bit fancier? What if I wanted to do something that, let's say I have some function. Let's say I have some function that looks like this. Let me draw some function that's, I should draw straighter than that. I should have some standards. So let's say that just my regular f of t, this is x. Actually, why am I doing x? This should be the t-axis. We're dealing in the time domain. It could have been x, and then this is, we could call this f of t. So let me draw some arbitrary f of t. Let's say my function looks something crazy like that. Now, what if I'm modeling a physical system? This is my f of t. What if I'm modeling a physical system that doesn't do this? That actually, at some point, well, actually, let's say it stays at 0. It stays at 0 for until some value. Let's say it goes to 0 until, I'll call that c again. And then at c, f of t kind of starts up. So right at c, f of t should start up. So it kind of goes like this. So essentially what we have here is a combination of it's 0 all the way, and then we have a shifted f of t. So at c, we have a shifted f of t. So it shifts that way. So how can we construct this yellow function, where it's essentially a shifted version of this green function, but it's 0 below c? This green function might have continued. It might have gone something like this. It might have, continued and done something crazy. But what we did is we shifted it from here to there, and then we zeroed out everything before c. So how could we do that? Well, just shifting this function, you've learned in your Algebra 2 or your pre-calculus classes, to shift a function by c to the right, you just replace your t with a t minus c. So this function right here is f of t minus c. And to make sure I get it right, what I always do is I imagine, okay, what's going to happen when t is equal to c? When t is equal to c, you're going to have a c minus a c, and you're going to have f of 0. So f of 0 should be the same. So when t is equal to c, this value, the value of the function should be equivalent to the value of the original green function at 0. So it's equivalent to that function value, which makes sense. If we go up one more above c, so let's say this is one more above c, so we get to this point. If t is c plus 1, then when you put c plus 1 minus c, you just have f of 1. And f of 1 is really just this point right here. And so it'll be that f of 1. So it makes sense. So as we move 1 forward here, we're essentially at the same function value as we were there. So the shift works. But I said that we had to also, if I just shifted this function, you would have all this other stuff. Because you would have had all this other stuff when the function was back here still going on, right? The function, I'll draw it lightly, it would still continue. But I said I wanted to zero out this function before we reach c. So how can I zero out that function? Well, I think it's pretty obvious to you. I started this video talking about the unit step function. So what if I multiply the unit step function times this thing? What's going to happen? So what if my new function, I call it the unit step function up till c of t, times f of t minus c. So what's going to happen? This, until we get to c, right, the unit step function is 0 when it's less than c. So you're going to have 0 times, I don't care what this is, 0 times anything is 0. So this function is going to be 0. Once you hit c, the unit step function becomes 1. So once you pass c, this thing becomes a 1. And you're just left with 1 times your function. So then your function can behave as it would like to behave. And you actually shifted it. This t minus c is what actually shifted this green function over to the right. And this is actually going to be a very useful way to look at, or a very usefully constructed function. And in a second, we're going to figure out the Laplace transform of this. And you're going to appreciate, I think, why this is a useful function to look at. But now you understand at least what it is and why it essentially shifts a function and zeroes out everything before that point. Well, I told you that this is a useful function, so we should add its Laplace transform to our library of Laplace transforms. So let's do that. So let's take the Laplace transform. Let's take the Laplace transform of this, of the unit step function up to c. I'm doing it in fairly general terms. In the next video, we'll do a bunch of examples where we can apply this. But we should at least prove to ourselves what the Laplace transform of this thing is. Well, the Laplace transform of anything, or our definition of it so far, is the integral from 0 to infinity of e to the minus st times our function. So our function in this case is the unit step function, u sub c of t, times f of t minus c dt. And this seems very general. It seems very hard to evaluate this integral at first. But maybe we can make some form of a substitution to get it into a term that we can appreciate. So let's make a substitution here. Let me pick a nice variable to work with. I don't know. We're not using an x anywhere. So might as well use an x. That's the most fun variable to work with. X. Sometimes you'll see in a lot of math classes they introduce these crazy Latin alphabets, and that by itself makes it hard to understand. But so I like to stay away from those crazy Latin alphabets. So we'll just use a regular x. Let's make a substitution. Let's say that x is equal to t minus c, right? Or you could, if we added c to both sides, we could say that t is equal to x plus c. Let's see what happens to our substitution. And also, if we took the derivative of both sides of this, or I guess the differential, you would get dx is equal to dt. Or, I mean, if you took dx with respect to dt, you would get that equal to 1. C is just a constant. And if you multiplied both sides by dt, you get dx is equal to dt. And that's a nice substitution. So what is our integral going to become with this substitution? So our integral, this was t equals 0 to t is equal to infinity. When t is equal to 0, what is x going to be equal to? Well, x is going to be equal to minus c. Actually, before I go there, let me actually take a step back, because we could progress. We could go in this direction, but we could actually simplify it more before we do that. Let's go back to our original integral before we even made our substitution. If we're taking the integral from 0 to infinity of this thing, we already said, what does this integral look like? Or what does this function look like? It's 0. We have this unit step function sitting right here. We have the unit step function sitting right there. So this whole expression is going to be 0 until we get to c. Right? This whole thing, by definition, this unit step function is 0 until we get to c. So everything's going to be zeroed out until we get to c. So we could essentially say, we don't have to take the integral from t equals 0 to t equals infinity. We could take the integral. Let me write it here. We could take the. I'll just use that old integral sign. We could just take the integral from t is equal to c to t is equal to infinity of e to the minus st, the unit step function, uc of t times f of t minus c dt. In fact, at this point, this unit step function is it has no use anymore. Because before t is equal to c, it's 0. And now that we're only worried about values above c, it's equal to 1. So it equals 1 in this context. I want to make that very clear to you. What did I do just here? I changed our bottom boundary from 0 to c. And I think you might realize why I did it when I was working with the substitution, because this will simplify things if we do this ahead of time. So if we have this unit step function, this thing is going to zero out this entire integral before we get to c. Remember, this definite integral is really just the area under this curve. right, of this whole function, of the unit step function times all of this stuff. All of this stuff, when we multiply it, it's going to be 0 until we get to some value c. And then above c, it's going to be e to the minus st times f of t minus c. So it's going to start doing all this crazy stuff. So if we want to take essentially find the area under this curve, we can ignore all the stuff that happens before c. So instead of going from t equals 0 to infinity, we can go from t is equal to c to infinity, because there was no area before t was equal to c. So that's all I did here. And then the other thing I said is that the unit step function, it's going to be 1 over this entire range of potential t values. So we can just kind of ignore it, right? It's just going to be 1 this entire time. So our integral simplifies to the definite integral from t is equal to c to t is equal to infinity of e to the minus st times f of t minus c dt. And this will simplify it a good bit. I was going down the other road when I did the substitution first, which would have worked, but I think the argument as to why I could have changed the boundaries would have been a harder argument to make. So now that we had this, let's go back and make that substitution, that x is equal to t minus c. So our integral becomes, I'll do it in green, when t is equal to c, what is x? Then x is 0, right? C minus c is 0. When t is equal to infinity, what is x? Well, x is, infinity minus any constant is still going to be an infinity. Or the limit as t approaches infinity, x is still going to be infinity here. And it's the integral of e to the minus s. But now instead of a t, we have the substitution. If we said x is equal to t minus c, then we can just add c to both sides. You get t is equal to x plus c. So you get x plus c there. And then times a function, f of t minus c. But we said t minus c is the same thing as x. And dt is the same thing as dx. Showed you that right there. So we can write this as dx. Now this is starting to look a little bit interesting. So what is this equal to? This is equal to the integral from 0 to infinity. Let me expand this out, of e to the minus sx minus sc times f of x dx. Now what is this equal to? Well, we could factor out an e to the minus sc and bring it outside of the integral, because this has nothing to do with what we're taking the integral with respect to. So let's do that. Let me take this guy out. And maybe just to not confuse you, let me rewrite the whole thing. 0 to infinity. I could rewrite this e term as e. Actually, let me write it this way. I'll do what was already in green, as e to the minus sx times e to the minus sc, right? Common base. So if I were to multiply these two, I could just add the exponents, which you would get that up there, times f of x d of x. Times f of x d of x. This is a constant term with respect to x, so we can just factor it out. We can just factor this thing out right there. So then you get e to the minus sc times the integral from 0 to infinity of e to the minus sx times f of x dx. Now, what were we doing here the whole time? We were taking the Laplace transform. We were taking the Laplace transform of the unit step function that goes up to c, and then it's 0 up to c, and it's 1 after that, of t times some shifted function, f of t minus c. And now we got that as being equal to this thing. And we made a substitution. We simplified it a little bit. E to the minus sc, times the integral from 0 to infinity of e to the minus sx f of x dx. Now, something about the tablet doesn't work properly right around this period. But this should look interesting to you. What is this? This is the Laplace transform of f of x. Let me write that down. What's the Laplace transform of well, I could write it as f of t or f of x. The Laplace transform of f of t is equal to the integral from 0 to infinity of e to the minus st times f of t dt. I mean, this and this are the exact same thing. We're just using a t here. We're using an x here. No difference. They're just letters. But this is f of t. This is f of t. E to the minus st times f of t dt. I could have also rewritten this, the Laplace transform of f of t. I could write this as the integral from 0 to infinity of e to the minus sy times f of y dy. I could do it by anything because this is a definite integral. The y's are going to disappear. And we've seen that. All you're left with is a function of s. This ends up being some capital, we could write some capital function of s. So this is interesting. This is a Laplace transform of f of t times some scaling factor. And that's what we set out to show. So we can now show that the Laplace transform of the unit step function times some function t minus c is equal to this function right here, e to the minus sc, where this c is the same as this c right here, times the Laplace transform of f of t, times the Laplace transform, I don't know what's going on with the tablet right there, of f of t. Let me write that. This is equal to, because it's looking funny there, e to the minus sc times the Laplace transform of f of t. So this is our result. This is our result. Now what does this mean? Let's see if we, backfilled it somehow. What does this mean? What can we do with this? Well, let's say we had the Laplace transform. Let's say we wanted to figure out the Laplace transform of the unit step function that starts up at pi of t. And let's say we're taking, I don't know, something that we know well. Sine of t minus pi. So we shifted it, right? This thing is really malfunctioning at this point right here. Let me pause it. I just paused. Sorry if that was a little disconcerting. I just paused the video because it was having trouble recording at some point on my little board. So let me rewrite the result that we'd proved just now. We showed that the Laplace transform of the unit step function t, and it goes to 1 at some value c, times some function that's shifted by c to the right, it's equal to e to the minus cs times the Laplace transform of just the unshifted function. That was our result. That was the big takeaway from this video. And if this seems like some Byzantine, hard to understand result, we can apply it. So let's say the Laplace transform, this is what I was doing right before the actual pen tablet started malfunctioning. If we want to take the Laplace transform of the unit step function that goes to 1 at pi t times the sine function shifted by pi to the right, we know that this is going to be equal to e to the minus cs. C is pi in this case, so minus pi s times the Laplace transform of the unshifted function. So in this case, it's the Laplace transform of sine of t. And we know what the Laplace transform of sine of t is. It's just 1 over s squared plus 1. So the Laplace transform of this thing here, which before this video seemed like something crazy, we now know is this times this. So it's e to the minus pi s times this, or we could just write it as e to the minus pi s over s squared plus 1. We'll do a couple of more examples of this in the next video where we go back and forth between the Laplace world and between the s domain and the time domain, and show you how this is a very useful result to take a lot of Laplace transforms and to invert a lot of Laplace transforms.